22个。
看得见吗
OK， 不错。哦。Masaki， Masaki 一样，他的 family name 跟我的一样。现在人不少了，有20多个了。
那可以开始了。
Okay, so let's start our morning session. So first speaker is Professor Zizhong Xing from iHealth, who will be talking about the neutrino mass and the Eukaryote interaction. Okay, let's welcome.
Thank you, Yimin. Good morning, colleagues. Let me first thank the organizers for giving me this opportunity to talk about neutrino mass generation and Eukaryote interactions. I will focus on the Arana neutrinos and type 1 seesaw mechanism. Oh, yeah, my first slide just wants to give you a preliminary feeling of neutrinos in the past 65 years, and especially after the discovery of neutrino oscillations in 1998. Thanks to the neutrino oscillation experiments, we have known quite a lot about neutrinos, the free mixing angles, the mass squared differences, and even preliminary data about CP violating phase. The next generation neutrino experiments will pin down the mass ordering and determine the Dirac CP violating phase. But on the theoretical side, no breakthrough has happened, unfortunately. And that's why Edward Wheaton was quite disappointed about 20 years ago, because there's no convincing quantitative model of neutrino masses. And a few years ago, Stephen Weinberg also expressed his willing to see the observed pattern of quark and lepton masses, but unfortunately, he didn't see this in his lifetime. So in this talk, I will first give some general remarks along the line of thought of Weinberg from 1967 to the last year. In the second part, I will cover two specific examples. One is about neutrino effective theories, and the other about modular symmetry. I'm very sorry for having no time to cover other topics. So first, let's look at the standard model. What's wrong with the standard model? You can see that the theoretical ingredients of this model is perfect. And everything is there, but its particle content looks very strange. No quark flavors, no neutrino masses, no flavor mixing, and no CP violation. The reason is simply that the structure of the standard model is too simple. In the beginning of this year, Weinberg said his style is usually not to propose specific models, but to make very general remarks, like the effective field theory. So that's to say, usually he didn't propose any specific models, but if he did, it should be the standard model. And we can imagine a seemingly wrong use of Occam's razor in the standard model because there's no right-handed neutrino field. So Weinberg simply cut out that part of particle content. So it's too simple. It's too simple. So in this case, if we want to introduce neutrino masses, the simplest way to do is to introduce right-hand neutrino fields into the standard model. Yes, we can do this. And in this case, we can assume right-hand neutrino fields may have very big self-interaction coupling, or equivalently, the Marana mass term. In this case, lepton number is violated, and the sectors of left and right-handed neutrinos should have a mass gap implying a flavor democracy in a proper basis choice. But we must introduce Yukawa interactions to bridge the left and right-handed sets and to give small masses to the light neutrinos. This is just the type 1 seesaw mechanism. And we like type 1 seesaw because this picture is well consistent with the spirit of Weinberg's effective field theory with a unique dimension 5 operator. So in this sense, I say that the type 1 seesaw in the landscape. You know Martha's conjecture about swampland for low energy effective quantum field theory and their relations with the UV theory, such as the string theory on quantum gravity at the super high energy scale. So I follow this concept and argue that natural seesaws from fundamental theory at the super high energy scale might be present. In this case, effective low energy neutrino mass models might be in the landscape if after we enhance the cutoff scales, we can finally reach that natural seesaws at the super high energy scale. And this was actually historically true. We can discuss, for example, Fermi's effective field theory for beta decays and to see how it can be extended to the Weinberg standard model. So here you see this, between these two, there's a gauge seesaw between the Fermi coupling constant and Weinberg's coupling constant for weak interactions. In this case, our question is, how about neutrino coupling interaction? And of course, we have introduced neutrino Yukawa interactions between the left-handed and right-handed neutrino fields. And we can diagnose the 6x6 Majorana neutrino mass matrix to determine the neutrino masses to identify their Majorana nature and to obtain the big charge current interactions in terms of flavor eigenstates of light neutrinos, which are the linear combinations of light and the heavy neutrino mass eigenstates. Of course, one can introduce the Euler-like parameterization of everything. And in this case, we must remember the 3x3 PMS active neutrino mixed matrix is not exactly unitary. And we can also follow the approach of Casas and Ibarra to make a factorization of the active stereo flavor mixing matrix, or effectively the so-called Dirac matrix. And we borrow this kind of inspiration from hadron physics. And of course, in this seesaw approximation, only the dimension 5 operator is responsible for the mass generation. Dimension 6 operators violates the PMS unitarity. But factorization has little to do with dynamics. So in this case, we can come back to Weinberg's conjecture made last year. He assumed that only the third family of fermions at the tree level Yukawa interactions. The others gain their masses via loop correction. But this is a very interesting model, but it's not valid for several reasons, as admitted by Weinberg himself. In this case, one may have somewhat different opinions. Fermion masses primarily stem from tree level Yukawa interactions in the standard model. The flavor mixing, a kind of mismatch between the Yukawa and the charge current gauge interactions, should originate at the same time as fermion masses. So this is our point of view. So in this case, of course, we seem to be on the right track. We know last year, CMS and Atlas collaborations have preliminarily measured the second family tree level Yukawa interactions, 6 decays to muon. So this is very good news. And some colleagues even consider the possibility to measure electron Yukawa interaction in the future, in the far future. So of course, it's really challenging, but for neutrino Dirac Yukawa interactions, it's absolutely impossible to measure in experiments because it's too small. So in this case, of course, we still have confidence on the tree-level Yukawa interactions for all the fermions. And for Majorana neutrino, we can use the lepton number violation to find the different ways, indirect ways to determine the Yukawa interaction. Of course, more challenges are coming from the flavor mixing, and in the quark sector, in the neutrino sector, both are quite strange. Need flavor symmetries or other dynamics to explain the observed pattern of quark and lepton flavor mixing. So now I come to the second part of my talk, and I will cover neutrino effective field theories and modular flavor symmetry. First, let me take a look at the neutrino masses in the standard model effective theory at the tree level. So we know the SMEFT is built with the standard model degrees of freedom, and the standard model gauge symmetry like this. And dimension 5 operator is unique. Dimension 6 violates unitarity of the 3x3 PMS matrix. Dimension 7, 8, 9, and so on. So many people have done some interesting works in this direction. For a given mass dimension 2n plus 5, there's only a unique operator that can give neutrino masses at the tree level. So in this case, of course, we can also consider the one loop corrections from the dimension 5, 6, 7, and so on operators and in the SMEFT framework. So I just show you this possibility. Of course, the loop correction is always small, but might not be that small. And because of lepton number violation, the higher dimension operators also show up in some interesting decay modes like the neutrino double beta decay. So here I show you the dimension 5, dimension 6 operators contribution. And a lot of works have been done in the literature, including Professor Yi Liao from Nankai University. And there are some other aspects of including lepton flavor violation in the SMEFT. The SMEFT with their neutrinos. I will not go into detail, but here I concentrate on neutrino effective field theory. Neutrino EFT is defined as an EFT after integrating all the heavy degrees freedom, like the heavy Majorana neutrinos in type 1 seesaw model. So here I consider type 1 seesaw with 3 red hat neutrinos. We can write down the Lagrangian this way. We integrate all the heavy degrees freedom at the tree level up to dimension 6 operators. We get this formula, and we know all the dimension 6 operators violates unitarity of the PMS matrix. And in the minimal unitarity violation scheme proposed by Andrews and other colleagues, the unitarity violation has been discussed. But that's the tree level result. And here we want to give a self-consistent calculation of lepton flavor violating processes like mu to E gamma at the tree level with dimension 5 and dimension 6 operators. And we do this, and you can find that the final result for the amplitude of these 3 diagrams inconsistent with the full type 1 seesaw model as observed last year by my student Li Zhang and myself. So in this case, we worried. The type 1 seesaw in the swampland, there's something wrong with this consistency between the effective seesaw model and the full type 1 seesaw model. The answer is negative. Actually, in the previous calculations, there is something missing. The reason is the missing of contributions from one loop match. So you can see from this blue box, and this is the operators from one loop matching. You have to take into account this contribution, and then you can get a total amplitude, which is consistent with the full type 1 seesaw peak. So now we are relaxed. So we believe that the type 1 seesaw is in landscape. it's a good digital picture, and its low energy effective field theory are also consistent. So later early this year, and Di Zhang and my colleague Xun Zhou wrote a very nice paper. They discussed the complete one-loop matching of the type 1 seesaw onto the standard model effective field theory. So to assure that the type 1 seesaw is in landscape. A lesson that one can learn from their calculation is it's highly non-trivial to see whether a neutrino effective theory is in landscape or swampland. So we must be careful in consider the matching condition. Okay, let me turn to the flavor symmetries. And flavor symmetry is argued to be a powerful guiding principle for neutrino mass model to determine the Yukawa structure. In principle, this is okay, but in practice, there's a lot of problems. And people have considered a lot of continuous or discrete flavor symmetry groups. But for the conventional approach, a big problem is about flavorons, assignments, and how to break these flavor symmetries. So here I show you two examples for Gard-Nielsen mechanism of this flavor symmetry of A4. So you can see in the conventional approach, you can determine the hierarchy of masses and flavor mixing patterns from the Gard-Nielsen mechanism. Or you can determine constant primary matrix of neutrino mixing class corrections. So these are their salient features. But here I mentioned the new development, the so-called modular flavor symmetry from string theory. And the modular symmetry was originally proposed by Altarelli, Ferrugiu, and recently highlighted by Ferrugiu. So its key point is very simple. It's just a kind of compactification of the 10-dimension string theory into 4-dimension standard model as 3 copies of torus. And those torus can be described in 2-dimensional plane with a modular parameter top. And this modular transformation is nonlinear. You can see the tau transformation is a kind of fraction. But the point is that the modular group has finite subgroups. And the quotient group of modular group and its principal congruence groups contain discrete flavor symmetry groups like S3, A4, S4, and so on. So that's why these modular groups could be used for neutrino mass model building, and the modular invariance be used as a flavor symmetry. And if we require the superpotential to be invariant and the modular transformation, then we can constrain the structure of Yukawa interactions. So this is the so-called modular form of Yukawa couplings. So in this case, as I said before, the realization of modular symmetry is nonlinear. So you cannot see the simple structures of Yukawa interactions. And here I show you an example given by Kobayashi and his collaborators 2 years ago, and a model in MSM with A4 symmetry without flavor. Another example has been discussed by Xin Wang in his talk in the parallel session on Tuesday. So for modular A4 symmetry, we can finally derive the patterns of Charles-Lepton, right-hand neutrino, direct neutrino mass matrices like this. And remember again that the physical meaning of complex modular parameter is unclear, and the flavor structures are not transparent due to a nonlinear realization of modular. And hence, a careful numerical fitting has to be done. So this is quite uneasy to me because we simply cannot see the structure, clear textures of those mass matrices. Here I list some recent papers, a lot of papers, and more than 60, more than 70, and many topics, including lepton quark flavor issues, multiple modular symmetries, and the generalization CP violation, double covering, fixed points, residual symmetry, and the Taylor potential, and even the eclectic that I don't know, and other topics. And many Chinese colleagues contributed to this hot direction. Okay, let me make summary. In the coming 20 years, I believe precision tests of fundamental Yukawa interactions of charged fermions remain a big challenge at the energy frontier. And the trivial neutrino Yukawa interactions, namely Dirac neutrinos, are experimentally impossible to be tested. And this possibility is theoretically unnatural either. So the banana nature of neutrinos is appealing, and the seesaw picture and its effective field theory consistent with the Weinberg's effective field theory spirit, and thus in the landscape. On the other hand, the modular symmetry differs from the conventional flavor symmetry in several aspects. In particular, the modulus parameter versus Cauchy-Gordon coefficients. And the latter allows us to obtain the constant flavor mixing pattern, and the former doesn't allow us to do so. But anyway, the modular symmetry offers a new string possibility to look at the neutrino Yukawa interaction. So this is good. Okay, thank you for your attention.
Okay, thank you very much. So a wonderful talk. So any question or comments? Okay, so if not, so let's thank Zizhuang again. Okay, thank you. Okay. So the next talk is the speaker is Jeffrey Lazar. He was talking about S-cube search for solar wind. So let's welcome. Okay.
Thank you.
I should stop the sharing.
Cool. I will start.
Okay. So, okay.
Do you see the slides in full screen mode?
Yeah.
Beautiful. Okay. Well, hello, everyone. Thank you very much to the organizers for giving me an opportunity to give this talk. Yeah. I will be talking about IceCube's most recent solar WIMP search. And I don't know if I introduced myself. Sorry, I'm Jeff Lazar, and I was speaking on behalf of the IceCube collaboration. And so what we're doing today, or what my analysis looks for, is for astrophysical signatures of WIMPs. And so the way one typically does this is by looking for, or I guess the mechanism by which one can do this is via WIMP annihilation, in which two WIMPs via some unknown mechanism, which is your theory input, turn into two standard model particles. And so these can be whatever you want, but sort of generically, any unstable standard model particles will eventually decay, or they'll decay, they'll interact, they'll hadronize into a number of, or into stable standard model particles. And so among these stable particles, only neutrinos are able to escape dense astrophysical environments. And so, so the name of the game in this is looking for an excess of neutrinos coming from the direction of places where WIMPs are expected to accumulate. So this is a very generic case. Any model which allows WIMP annihilation will produce neutrinos. But it's possible that there's perhaps a more intimate connection between dark matter and neutrinos. And so the reason for thinking this might be the case is that the two main weaknesses in the standard model are the non-zero neutrino mass and the lack of a dark matter candidate. And it's always sort of, it's preferable to solve two problems for one. It makes the theory seem less contrived and such. Somewhat recently, what are called scotogenic models have become popular, These models were pointed out as early as 2006, and these are ones in which neutrinos gain their mass via loop level interactions with dark matter. Unfortunately, I will not be able to go into this too much today, but I wanted to point it out as a tantalizing possibility. So we're looking for neutrinos, and to do that, we obviously need a neutrino telescope. Fortunately, I'm a member of the IceCube collaboration. And so IceCube is a gigaton scale detector located at the geographic South Pole. So it's basically a cubic kilometer of very, very clear ice instrumented with cubic kilometer of ice instrumented with light detectors, which we call DOMs, digital optical monitors. And I have a little diagram here. It's a PMT with onboard digitization equipment. And these are able to look for the footprint of neutrinos by seeing the light produced by charged particles that are made in neutrino interactions. And so IceCube has sort of a main array, which we call IceCube, and a subarray, which is more densely instrumented and more sensitive to lower energy neutrinos, called deep core. So IceCube is this whole blob here, and then deep core is this little thing around here. And so even though we say that IceCube is a neutrino telescope, ultimately all it can see is light and time. And so what do these neutrinos or particles look like in the detector? So we have three basic morphologies, we call them. They're the shapes that the particles make. So here I show what we call a track. And so each of these circles is a DOM, a light detector. And then if it's not filled in, it did not see light. If it is filled in, it did see light. The color is the time, and the size is the amount of light. So this particular particle came in from the top left to the bottom right. And this is what we call a track because it forms sort of a track-like, line-like morphology in the detector. And these are created when muon neutrinos undergo charge current interactions and create muons. We also have what we call cascades, which are these spherical morphologies. These are created when by electron charge current interactions or any neutral current interaction. We also have double bangs, which are sort of you get two cascades, and these are created by when tau neutrinos create a tau here, and when the tau decays over here. So you get these two sort of point-like depositions of light. And so in the detector, those were cartoons. This is what they look like. So this is these are sort of medium energy for IceCube events. This is a 21 TeV electron. You see it has that sort of spherical look to it. And this is a 7 TeV muon. And you can see it has this line going from here to here. And so now that's sort of the background of all of this. And now what is my analysis actually doing? We're looking for dark matter capture and annihilation. So the way this works is you have a dark matter particle, which I sort of show as a chi here, floating around in the galactic dark matter halo. It can interact and it can scatter off protons and neutrons. This can happen generically. It can lose energy and may become gravitationally captured in this interaction. And then from there, it will have further scatterings and it will eventually sink to the center of the sun. This will lead to an overabundance of WIMPs at the center of the sun. And then these WIMPs, sort of generically as well, can annihilate, creating the standard model particles, which will inevitably lead to neutrinos, as I outlined earlier, which we can detect at Earth. So the name of the game is look for more neutrinos than expected coming from the direction of the sun. And so what sort of parameter, what are we probing with such an analysis? And so we can get a handle on this by looking at the differential equation, which governs the number of WIMPs in the sun. So on the left-hand side, I have the time derivative from the number of the WIMPs in the sun. This blue term is the capture rate. So that's how WIMPs can enter the sun. And WIMPs can leave the sun either by annihilating, which is the second term in green, or they can annihilate by, or they can leave the sun by evaporating, basically just getting kicked out. And that's the yellow term. And so this yellow term, sorry, the green basically sets the normalization for the rate at which we see neutrinos, since we see neutrinos because of the annihilation process. But we expect this to be an equilibrium for stars the age of the sun. And we also expect the evaporation rate to be negligible above a few GeV, which is the regime that we are in for this analysis. So we can safely set the left-hand side of this equation and the last term to 0. And this leads us to conclude that the annihilation rate, which sets the rate at which we see neutrinos, is proportional to the WIMP nucleon cross-section, which sets the rate at which they are captured. And this is sort of a nice thing because this is the same parameter which is probed by direct detection experiments. So this sort of gives us two complementary ways to see or to probe this parameter. And this is complementary both in that they probe different parts of the velocity distribution. So indirect detection, which is what IceCube can do, probes the sort of lower velocity WIMPs, and this is because they're easier to capture. And direct detection probes higher velocity WIMPs because they will deposit more energy in your detector, or they'll deposit more energy in your detector. So there's a complementarity over the WIMP velocity distribution, but there's also a complementarity over the WIMP mass range. So here I show limits from on the WIMP nucleon cross-section for PICO, which is a direct detection experiment. And you can see it's most sensitive at these lower masses. Excuse me. And I show limits from IceCube in the higher mass, which are more constraining in the higher mass region, which come from indirect detection. Yeah, so that's the gist of the analysis. But so yeah, I guess these are all the relevant fluxes to this analysis. So in the purple, we have some sort of demonstrative example cases of the flux of neutrinos from dark matter annihilation. So this is for 3 different neutrino masses, or 3 different dark matter masses. We also have fluxes of different, known neutrino fluxes. So these blue crosses are conventional atmospheric neutrinos. Red crosses are the astrophysical neutrinos as measured by IceCube. And as you can see, because of the opacity of the sun, or the sun becomes opaque neutrinos at a few TeV. And so we don't make it to this region in which the astrophysical neutrinos are relevant. We only get to, our only real background is atmospheric neutrinos. There is, however, one less considered source of neutrinos, which is the solar atmospheric neutrinos. And this is neutrinos produced via cosmic ray interactions in the solar atmosphere. And although the flux is at the same level as the conventional flux, it's suppressed by the solar solid angle. And so it is yet undetected, but is still, in theory, a background for this analysis, and we do include it. So for this analysis, we want to sort of probe all energies all WIMP masses that IceCube can. And so this roughly goes from 10 GeV to 10 TeV. However, as you go to these lower masses, directional reconstruction becomes very challenging. So oftentimes in IceCube, you'll see these beautiful tracks that you can definitely point back to the direction the neutrino came from. But as you move to these lower energies, it becomes much more challenging, and you only get a few only a few DOMs will see light in your detector, and so it becomes much harder to reconstruct the direction. So here I show sort of an example of this at 200 GeV. This is an electron, and this is a muon. And so you lose the advantage. Oh, and the muons are usually much easier to reconstruct the direction. So you lose sort of the advantage of only having a muon selection at high energies as you move to these lower energies. Also as you move to lower energy, or just in general, the cascade channel signal to background ratio is about 10 times better. And so these 2 points together sort of tell us that if we want to do all energies, we should do all flavors at the lower energies. And so that's what we've done. We've combined a low and high energy selection, which is to say a deep core and a full ice cube detector selection for this analysis. So here I show the expected distribution for an example, the expected event distribution as a function of distance from the sun on the y-axis and reconstructed energy on the x-axis for an example dark matter case. And so here I show the distribution, just a 1D projection of the distribution in distance from the center of the sun. And as you can see, the red, which is the high energy selection, is much more peaked near the sun, while the blue, you almost can't see it. The angular reconstruction is so poor at these energies that it's difficult to see under this. And then additionally, I show a projection in the reconstructed energy. And very interestingly, and I will come back to this, you see this big gap in between the two selections. So this hints that we may be missing something in between these, even though we've sort of tried to combine a low energy and a high energy. There may be a regime in the middle that we're not targeting. So here I show sensitivities for this analysis. So a few things to point out about this. So I show sensitivities to the WIMP nucleon cross-section as a function of Doppler mass. So for BB bar, WW, and tau tau, these are sort of our benchmark channels. A few things to point out. One is this, this huge factor of 40 improvement in sensitivity for the BB bar channel, and a sort of more modest factor of 4 improvement for WW and tau tau. The other is that we have basically world-leading sensitivities over 3 orders of magnitude in dark matter mass, which is great. And then one sort of less flattering thing is that we see this huge kink, this huge loss of sensitivity in the 100 to 300 GeV range for the dark matter mass. This is a particularly important range, and this is a direct product of the sort of gap between the two selections. So we are working to improve this, but that's sort of an ongoing work at this point. But first, you see a very large improvement in one channel and not in others. You think something might be going wrong. And so I think I should explain where this comes from a bit. And it comes from a sort of the new way that we calculated our signal fluxes. So we did this with a package that we used that we developed for this analysis. So it's called Caron, and it calculates neutrino yields from dark matter annihilation and decay. And it couples Pythia 8 to an updated calculation of the electroweak correction. It's Python based, which is convenient. So yeah, and if you click almost anything in the slide, you'll be able to get to the GitHub, and I encourage all of you to try it out and play with it. And we're trying to add as many features as we can. So if there's a flux that isn't included that you would like to see, please let me know. But this electroweak correction that we've added turns out to be extremely important. And so this is basically a so-called correction arising from the fact that above the electroweak scale, you're able to radiate W and Z gauge bosons much in the same way that you can radiate photons at lower energies. And so this sort of has two different ways that have, two different things that have been called the electroweak correction in literature that are a little bit different. There's one where your final state standard model particles radiate these. And so that is sort of, I guess, model independent because it's only includes the standard model. But there is also model dependent internal Bremsstrahlung in which you can radiate W and Z's. And so that requires a model. So this top one is the model independent, but it also, depending on the particle, the sort of theory input, you may get this additional radiation that could add. And so the one that we have included in this software is of the former case. It is of the standard model only case. And basically what they do is they take the standard model primary products at the dark matter scale. Excuse me, they evolve them down in energy using the DGLAP scale. And they eventually match them on to Pythia at 100 GeV via this sort of small phase space integration. And so this is sort of the magic of the calculation. But so this includes the full physics of the standard model and sort of matches onto Pythia in the range in which it has been extremely well vetted by collider experiments. So very technical. What does this mean? So here I show the spectra for BB bar in the top row and WW in the bottom row for 3 different dark matter masses. And you can see in the hadronic channels, which is to say the BB bar, as you move to higher and higher energies, you start to see these 2 groups forming. Each line is a different sort of event generator. Pardon me. So you see those which don't include the electroweak correction sort of hanging together here, and you see those which do include the electroweak correction achieving, going together, and at 10 TeV having a factor of 10 to 20 larger flux over the whole energy range. So this is order of magnitude increase in flux from including this correction. And then if we look at the WW, there's sort of more modest increases, and the electroweak correction makes the spectra a little bit softer than without. And so with that being said, I'm very excited to share with you sort of new results from IceCube. So recently I unblinded only the high energy portion of this analysis. And so here are new limits. So this is the limits on the spin-dependent nucleon cross-section as a function of mass, and I compare them to previous IceCube results, which were world-leading. And so we see around here a factor of, in fact, 50, not 40 improvement in the previous limits, and a factor of 3 to 4 in the WW and tau channels. So this is very exciting. We are, currently, it's exciting to see this large of improvements in the limits. But we are obviously not satisfied there. We still have this large gap in between the low and the high energy selection, and we are looking to improve upon that. So I'm in the process of developing a new selection, a medium energy selection, to target the gap which I previously showed between the 2 selections. And this is expected to fix the loss in sensitivity in the 100 GeV region. Towards this goal, we're sort of doing a 3-step process which mimics the previous IceCube solar WIMP analysis. And we're using a filter designed especially for solar WIMP analyses. We are using a BDT to filter out, to differentiate atmospheric muons from neutrinos. So here I show preliminary results from that. So as the orange line is the neutrinos, the blue line is the muons, and as you can see, the neutrinos are clustering over here, the muons over here, and so it is effectively, differentiating them. And then this is undergoing final optimizations, but we eventually want to develop another BDT to differentiate the signal in the background neutrinos. So this is coming soon. It should be, wrapping up soon, and then we can unblind the full event selection. So in summary, the solar WIMP searches that we're carrying out are complementary to direct detection searches in that they probe different mass ranges and different ranges of the velocity distribution. Our current sensitivities are world leading over 3 orders of magnitude. And in particular, there are large increases seen because of the new software which we developed for this analysis. The current high energy results show a 50% improvement over previous limits, and we're finalizing the final portions of this analysis, and we'll have further results coming soon. So with that being said, I once again, flash the propaganda plots that these are the current limits, which are world leading, and these are the sensitivities to come in the future, which we hope will also, be improved on even further. With that, I would like to thank you all for your attention and welcome any questions.
Okay, thank you very much. It was a very nice talk. So any questions or comments?
I have one.
Okay.
So yeah, probably a trivial question. A very nice talk, by the way. Why do you probe spin-dependent scattering cross-section and not spin-independent?
So we are, able to probe both, but we are not competitive with direct detection, like noble gas xenon, like noble gas direct detection experiments on spin independent. This is because the spin independent cross section is greatly enhanced by having a free electron, and so in the sun it's mostly hydrogen which has a free electron, and so you're able to capture that very efficiently. Whereas you can't in noble gas detectors. And in fact, I think it's the case that like nucleon for nucleon, we have the same sensitivity, but because they're able to, but sensitivity increases like A squared. And so because they just have heavier gases, they are much more sensitive to the spin independent cross section.
Thank you.
Yeah.
So, any other questions? So if not, let's thank Jeffrey again. So very nice time, very nice talk. So thank you, Jeffrey. Okay.
Yes, thank you very much, and thank you everyone for listening.
So next speaker is Professor Mary Angela Licenti. She will. We're talking about galactic probe for dark sector physics. Okay, let's welcome. Oh, okay, okay. So from your name, so I guess that you are a female professor. Okay.
Yes.
Okay.
Great. Okay, so let me just share my screen. Excellent.
Yeah, okay.
Okay. So I want to start by just thanking the organizers for the opportunity to speak virtually here today. It's always really nice to be able to connect with people, even on Zoom these days, and I hope you are all doing well. In my talk today, I want to be discussing ways in which we can use galactic physics to test models of dark matter. And in particular, I want to focus on the class of dark matter models referred to as dark sectors. So when we talk about dark sectors, we are thinking of the standard model as being in a separate sector to all of the dark matter and also any additional dark force carriers that might exist. And these two sectors might be connected to each other, communicate with each other through some additional mediator particles. Dark sectors are a fairly generic and well-motivated class of theories. They're distinct from the standard WIMP scenario. In the WIMP scenario, we would put the dark matter candidate within the standard model sector. But there's a lot of really interesting phenomenology that arises from these kinds of dark sector models. So when we talk about a dark sector, there's two key elements that we need to describe. The first is the mediators. And so this is essentially a portal that allows communication between the two separate sectors. And this isn't anything goes. The types of portals that we can write down are restricted by standard model symmetries. And on the next slide here, I'm just summarizing some important portals that have received a lot of attention in the literature recently. These include a vector portal, dark photons, sort of the canonical example there, an axion portal, the Higgs portal, neutrino portal, and so forth. The second important quantity that we need to characterize when we talk about a dark sector is what's actually going on inside of the sector itself. So how many different new particles are there, matter particles? Are there additional force carriers, and so forth? The details of the structure in that sector will affect how the dark matter is produced in the early universe. They can potentially lead to self-interactions and dissipative interactions between the dark matter particles, and they can also affect possible discovery channels for the dark matter. So let's consider just a very simple toy model where I have a single particle in the dark sector, which I'm calling here DM, and a standard model particle shown here as just SM, and a mediator that is in the portal. So here are just a variety of different ways in which the dark matter can interact with standard model particles or with itself. And depending on which diagram we look at, different phenomenology results. So for example, the diagram in the top left is essentially setting the abundance of dark matter in the early universe. As we move over to the right, this diagram here allows for dark matter direct detection in terrestrial experiments. So for example, maybe dark matter interacting with the nucleon or with an electron in a target. The diagram here on the rightmost diagram is dark matter annihilation. And then these bottom two diagrams are referred to dark matter self-interactions and also self-interactions with additional dissipation of energy. And for the rest of this talk, I'm really going to be focusing on scenarios such as the bottom two, and actually really only focusing on the leftmost just because of time constraints. But the reason that I'm focusing on these two is that galactic physics, galactic probes, are really an ideal way of testing this particular question about dark sectors. So they are going to be highly complementary with terrestrial searches that are going to be looking for dark matter interactions with the standard model. And they're going to help us answer questions about what kinds of new forces might exist in the dark sector itself that allow any kind of new self-interactions to occur. The types of phenomenology that arise in these cases can vary. And in the case where we have dissipative interactions, which is the second diagram here, you get very interesting substructure that can arise in a galaxy. It's actually it's a very interesting scenario, and I wish I had more time to talk about it. A lot of work has been going on in this area recently. But as I said, for the rest of the talk, I'm going to focus specifically on the case where the self-interactions are elastic and kind of work through how we think about that problem, the kinds of physics that are occurring on these galactic scales, and the constraints that we know are there, as well as some potentially intriguing hints for new physics that we want to be exploring further. So when we talk about self-interactions in a galaxy, we're essentially in order for those self-interactions to be relevant, it immediately points us to a particular cross-section for the interactions to occur at. And this was first pointed out in the inaugural paper on the subject by Spergel and Steinhardt. So if we ask simply the question, over the age of the universe, let there be one self-interaction near the center of the galaxy, what cross-section must the dark matter have in order for that to be true? The result is that it would be roughly cross-section over mass of the dark matter of 1 centimeter squared per gram. So that gives us a target. Cross-sections roughly on this order will end up affecting the distribution of dark matter on galactic scales. And what's particularly intriguing is that this is a typical type of cross-section that arises in dark sectors that have light mediators. So just as a very simple example, if you have a 10 GeV dark matter particle with a 10 MeV mediator, say maybe a dark photon mediator, coupling roughly electroweak strength, then you get 1 centimeter squared per gram. As a benchmark model that I'll keep referring to over the course of this talk, just as for concreteness, is a scenario such as illustrated here on this slide. So where we add an additional mediator, that mediator could either be a scalar or a vector, and allows for self-scattering of the dark matter through this T-channel diagram illustrated here. And this scattering is described by a Yukawa potential in the non-relativistic limit. So the actual details of that scattering process are that the self-scattering is velocity dependent and anisotropic. And that velocity dependence is actually really quite critical. So on the right here, I've written down what that differential scattering cross-section is. And there's 2 free parameters that come into play here. There's this sigma naught in the numerator, which essentially is a measure of the overall strength of that scattering and depends on the fundamental parameters in the theory as written down here. And then the other free parameter is omega, which is a velocity scale. Now, the fact that there is a velocity dependence to the self-scattering essentially ends up dictating over which velocities that scattering is going to be relevant for. And that tells us which systems are going to be the most interesting ones for searching for that kind of interaction. So in the diagram here on the left, I have, I'm just plotting the cross-section on the vertical axis. It's a function of velocity on the x-axis. The colors just represent 4 arbitrary scenarios, which have different values of the sigma naught parameter as well as this velocity scale omega. And indicated here on the top are the relevant velocity scales for different kinds of systems. So for example, dwarf galaxies have dark matter moving around at velocities of roughly tens of kilometers a second. The Milky Way has velocities of roughly hundreds kilometers per second, and galaxy clusters is more on the order of thousands of kilometers a second. And you can see that depending on the scenario that we look at here, you might see the self-scattering in some systems, but not in others. So for example, in the green scenario, the self-scattering would be evident across all different systems, dwarfs, Milky Way clusters. But in the case where we have the blue scenario, then the self-scattering might only be manifest on dwarf scales and would not be evident if you look at a Milky Way or a cluster system. So one of the key things when we talk about self-interacting dark matter is the need to actually be looking across multiple different systems on galactic scales in order to be able to understand what the velocity dependence of the scattering cross-section could potentially be. So moving forward, I'm going to be essentially building on this one diagram here. So I just want to take a moment to introduce it because we're going to use this as sort of the key summary of where the field is at the moment and where we're going to be able to take this moving forward. So on the x-axis of this plot is log base 10 of the sigma naught free parameter, where so specifically sigma naught divided by m chi. And then on the vertical axis is the velocity scale for the self-scattering. So when we look up here in the limit of large values on the y-axis, that's going to be the limit of velocity independent scattering cross sections. And just to kind of put some, give you some intuition for where models fall on this plane, this dashed line here indicates the regime, the boundary between the regime up here where the physics, the scattering is perturbative, and then the regime down here where it's non-perturbative, specifically for the choice of coupling alpha D that gives the correct freeze-out abundance for the dark matter. And for illustration, we're also showing here where a dark matter mass of 1 GeV would fall for this choice of coupling, and then also where a 1 NeV mediator mass would fall. So, you can see from the values here that we're talking about very light mediators, very light dark matter particles. Again, sort of consistent with what we expect for these dark sector type models. So let's start filling in this plane and reviewing the current status of the field. So first, I want to start with constraints that arise from looking at galaxy clusters and galaxy groups. As I mentioned earlier, the dark matter in these systems is moving at velocities that are on the order of 1,000 to 2,000 kilometers a second. And the constraints here can be quite strong. The sort of typical one that we often think about when we hear about self-interacting dark matter is the bullet cluster. We all have that picture in our mind. And other kinds of merging clusters like bullet end up constraining the cross-section, self-interaction cross-section, to be less than about 2 centimeters squared per gram. There are challenges associated with analyzing two clusters that are in this sort of very dynamic state where they're merging together. And it turns out that you can actually get better constraints by looking at isolated clusters. And in that case, the constraints can be as good as like 0.2 centimeters squared per gram. So on the left here, I'm actually showing the most current constraints from relaxed groups and relaxed clusters. And what you can see is that they very strongly rule out this regime up here where you have velocity independent scattering for the cross sections shown here. Good. All right. So now we're going to continue moving forward and start asking about the physics that arises in the white space that's left behind once we consider the cluster physics. And to do this, we need to take a moment and just reflect on what happens when you allow for self-interactions inside of a dark matter halo. The physics here is actually quite beautiful and quite intricate, so I do want to take like a moment to go through it. So the first stage of what happens is core formation. So you have self-interactions in your dark matter halo, and those self-interactions transfer heat inwards into the center part of the halo, and that ends up forming an isothermal core in the center. So we often think about cores associated with SIDM. This is precisely that picture there. Importantly, the size of the core is going to be correlated with the amount of baryons that are in the galaxy. If you have a galaxy that is baryon dominated, the presence of the baryons creates a deeper gravitational potential well, which ends up decreasing the size of the core, and in some cases, just making the galaxy dark matter distribution look cuspy. You can see this in the simulation results shown here from Robles et al. The cyan line here shows a scenario where you have a dark matter only simulation with self-interacting dark matter, and you get a very large core. And in contrast, the purple line shows an SIDM simulation where you include a baryonic disk in addition to the self-interacting dark matter, and the presence of that additional gravitational potential well results in essentially almost a cuspy profile in that case. This tight link between the size of the core and the amount of baryons in the system is actually very important and has been proposed as a potential solution to the galaxy diversity problem. The galaxy diversity problem is just another way of restating the core cusp problem. The statement can be summarized by this image here. So this is just showing rotation curves for a variety of galaxies in the Spark data set. All of these galaxies essentially have plateau at the same final circular velocity. But you can see that there's quite a bit of difference between all of them. In some cases, such as the blue, the rotation curve rises very rapidly. In other cases, it rises much more slowly. So any dark matter model needs to be able to adequately explain this diversity in the rotation curves. And SIDM can achieve this. So in particular, the steeply rising curves here are associated with higher surface brightness galaxies. So those would be the ones that have more baryons. where the core size would be smaller. And then the red curves would be are associated with the low surface brightness galaxies. Those are the ones with fewer baryons where the SIDM halo would be cored. So SIDM does provide a potential solution to the galaxy diversity problem, although it's not the only way in which you can resolve this particular issue. Okay, so we've talked about core formation, but that's actually not the final state for the halo. Once you do form this isothermal core, it's actually not stable. And after a certain point in time, will start to collapse again. So when that happens, when the heat flow changes direction and the self-interactions start to transfer heat outwards. In this case, the core starts heating up, it shrinks, and you start getting this accumulation and sharp rise in the density very close to the center of the dark matter halo. For an isolated galaxy, the time scale for this gravothermal collapse to occur is very long. And essentially, this is something that's irrelevant on those time scales. However, if you put a galaxy, like a dwarf galaxy, inside of another halo and it's tidally disrupted, that will reduce the collapse time and actually to the point where a gravothermal collapse can occur on relevant and observable timescales. This picture can potentially explain the range of observed central densities for Milky Way dwarf galaxies. So for example, here I'm showing a plot from work by Kaplingat et al. The y-axis is the central density of dwarf galaxies in the Milky Way. Specifically, rho 150 is the dark matter density within 150 parsecs of the center of the dwarf. And on the x-axis is the pericentric distance of the dwarf to the center of the Milky Way, so essentially its closest approach. And the different colors here indicate different dwarf galaxies. And you can see that there's a correlation between the inner density of the dwarf and its pericentric distance. So some dwarfs like Draco and Ursa Minor, which are located up here, have very large central densities and have are pretty close to the center part of our galaxy, whereas others like Fornax are much further away and have smaller central densities. Gravothermal collapse can account for this behavior because with the reasoning being that for these systems that approach closer to the center of the Milky Way, they have undergone more tidal stripping that accelerates gravothermal collapse, leading to a cuspier profile, compared to those dwarf galaxies that are further away and have undergone much less tidal stripping. So the gravothermal collapse timescale for a Fornax-like galaxy would be much longer than that for a Draco-like galaxy. And this has been schematically confirmed using some simulations. So on the right here is a result showing that for a Fornax-like galaxy, you get no gravothermal collapse and you still have a large core. Whereas for a Draco-like galaxy that has undergone considerable tidal stripping, you do get gravothermal collapse and you have much more density in the central part of the galaxy. Good, okay, so now we can come back to our parameter space here and ask, how can we use some of these systems like dwarf galaxies in the Milky Way to add additional constraints? Draco is a good example. As I mentioned on the previous slide, it has a very large inner densities. So that means that we have a requirement where any heating of the isothermal core should not reduce Draco's present-day central density more than 2 sigma below its measured value. And that's a very conservative statement. If we make this conservative statement, it translates into a bound here that's shown in blue. So it extends further down to lower velocity scales than would be probed by clusters and groups. That makes sense because now we're asking questions having to do with a dwarf galaxies where the velocity of the dark matter inside the dwarf is order tens of kilometers a second. Now, as I've drawn this here, I'm assuming, just for simplicity and also to make this bound very conservative, that there has been no gravothermal collapse that's occurred. If we were to properly model the gravothermal collapse, that could potentially end up making this bound even stronger than it should be. And that's ongoing work that we are currently pursuing. Okay, so next I want to discuss a little bit in more detail what happens as the dwarf galaxy actually falls into a host that's like the Milky Way. In this case, the dwarf galaxy is going to be cored because it's dark matter dominated, and the host galaxy is going to have a cuspy dark matter profile because it's baryon dominated. And SIDM can significantly affect the orbit of the dwarf as it falls in. There are two dominant mechanisms that can cause this. The first is tidal stripping. Specifically, the dark matter in the dwarf galaxy will be preferentially removed as the dwarf galaxy falls in if its density profile is cored. So this means that mass loss is going to be more pronounced for a cored density profile, leading to more tidal mass loss for an SIDM scenario. The second important effect comes from ram pressure evaporation, which is what occurs when dark matter in the dwarf interacts with dark matter in the host galaxy. So you can have these kinds of self-interactions occur, which would then essentially end up kicking the dark matter out of the dwarf galaxy, effectively evaporating it away. In this case, the mass loss is occurring from the scattering between the dark matter in the dwarf and the host, and will preferentially occur near the central part of the dwarf galaxy. So you'll get very efficient mass removal over the entire extent of the dwarf as it falls in. So I will just quickly sort of throw this up here, just in lieu of time here. So this is just showing some modeling that was performed of what happens to the mass of a galaxy as it's thrown into a Milky Way-like host. And the different lines here are comparing how much mass is lost if you have CDM dark matter or different SIDM scenarios. So the CDM is shown in dashed colors, and the SIDM is shown in solid. The difference between the blue and the red is the pericentric distance of the dwarf galaxy. And what we can see when comparing the blue lines to the red lines is that SIDM interactions will remove more mass compared to CDM in that dwarf galaxy, especially when pericentric distances are smaller. And also in some extreme scenarios, as indicated here by this yellow line, the SIDM interactions can be so strong that the ram pressure evaporation just dominates, and the galaxy, the dwarf galaxy, would just lose so much mass as it falls in compared to what you'd expect for cold dark matter. So this is a very simple analysis, but it does suggest that we can use information about the orbital properties of dwarf galaxies to tell us something about the microphysics of the dark matter particle. And that this is really arising from the fact that these are kind of like particle colliders on galactic scales. We have dark matter that's interacting with each other within the dwarf galaxy, but also between the dwarf and the host galaxy. There are a variety of effects at play, and all of them effectively lead to important differences in the orbital properties between CDM and SIDM. So taking this into account, there's an additional constraint that we can put down on this plot. We saw earlier that ram pressure evaporation can effectively remove a lot of mass from dwarf galaxies. So we can again place a conservative constraint by requiring that ram pressure evaporation not remove so much mass from the central regions of Draco to be inconsistent with observations. And doing so places this additional constraint shown here in the top right. It's not stronger than the groups or clusters constraint, but that's where it would fall. So all of this taken together points us to an important conclusion. So when we look at this range of parameter space, the region that's surviving is this white region here. And so what this is telling us is that when we take the constraints from dwarf galaxies in the Milky Way, couple them with constraints from groups and clusters, galaxy groups and galaxy clusters, we are led to conclude that if we have self-interacting dark matter, we need velocity-dependent cross-sections. And we also are going to be falling in a region of parameter space where gravithermal collapse is going to be an important effect and needs to be properly accounted for. So this is already giving us a target. This gives us a clear target for what we want to be probing moving forward. And there's a variety of different angles that we can use to further search for dark matter in this regime. So in a variety of works in progress with students and postdocs, we are looking at carefully analyzing properties of individual Milky Way dwarf galaxies. What I've shown here in this work, which was led by postdoc Oren Sloan, focuses on the Draco dwarf galaxy. We've also looked at several others, Ursa Minor, Segway, but we want to do moving forward is a full Bayesian analysis, stacking the contributions of all of these dwarf galaxies and seeing just how much far we can push these bounds. The second avenue is to actually study population statistics of satellites around Milky Way-like hosts. So as I discussed earlier, the orbital properties of dwarf galaxies are expected to be different, CDM versus SIDM. So precisely in this region here, we'd expect to see different distributions of dwarf galaxies around Milky Way-like host galaxies, Milky Way-like hosts. And then the last is to understand the implications of all of these results for lenses in galaxy clusters. The final 2 points here are quite relevant given some data that has been coming online just recently. On this slide here is work from Carlston et al. They have been looking and gathering data on a sample of Milky Way-like galaxies in the local group. And so they've essentially been counting up the number of dwarf galaxies as a function of the projected radii in each of these systems. Their data is shown in blue, and the orange is a CDM prediction from the Illustris simulation. And it's quite incredible that they're already accumulating this data for this number of systems in the local group. I mean, these dwarf galaxies are all quite faint. But also there's some intriguing behavior here in quite a few of these systems. The dwarf galaxies appear to be a bit more centrally concentrated than you might expect from CDM, at least from the orange bands. And so this is something that needs to be understood in greater detail, understanding the baryonic effects of this, the implications of that for CDM, and then also understanding what the SIDM predictions would be for cases like this. And lastly, I'll just end by showing some recent results from Meneghetti et al. This is looking at gravitational lenses about clusters. So on the left is what they are observing in their data, and on the right is CDM simulation. These dots that you see here are substructure lenses in the clusters. So these are essentially like little galaxies that are in the cluster itself. And what they're finding is that the cluster substructures lens more efficiently than you'd expect for CDM. And you can sort of see this by eye just from the fact that the dots in the left panel are much more pronounced than expected from the CDM simulation. And some recent work by Yang and Yu, some theory work, suggests that this can perhaps be possible in the SIDM framework if you have gravithermal collapse in your halos that are falling in, substructure halos that are falling in, because that could make them more centrally concentrated, such that they would lens more efficiently. So I will end here on the summary slide. Let me just restate that when we think about SIDM physics on galactic scales, there's a variety of different effects that are all at play. We have this beautiful picture of heat transfer inside the halos, which determines whether or not we have core forming or gravithermal collapse. We have this interesting behavior between interactions between dwarf systems and the background halo, leading to different behavior for tidal stripping, and we get ram pressure evaporation. And when we take all of that together and look at where that points us to, we're finding that these that galactic probes are suggesting that in the context of SIDM, we need velocity-dependent cross-sections with gravothermal collapse. And our way to sort of really target this moving forward involves some really exciting data that's coming online now, both having to do with individual Milky Way dwarfs in our system, dwarf galaxies in other hosts in the local group, and combining all of this with studies coming out on galaxy clusters. So I will end here, and I'm happy to take any additional questions. Thank you.
Okay, thank you very much for a very interesting talk. So any questions or comments? Okay, if not, so let's thank Mary Angela again. Okay, thank you very much. Okay, thank you. Okay, so next speaker is Professor Qiang Yuan. He will show us progress of dark matter particle explorer. Okay, let's welcome. Okay.
Yeah. Hello. So can you hear me?
Yeah. Okay.
Okay. So you can see my slide.
Okay. Yeah.
Okay.
Good.
Good.
Okay.
Good. Okay. So thanks the organizer for giving me this opportunity to share with you some progress of the DAMP project. The full name is Dark Matter Particle Explorer. So I'm from the Purple Mountain Observatory. So our collaboration is made up of basically 10 institutes, so 5 from China and 4 from Italy and 1 from Switzerland. This is the outline of this talk. I will introduce briefly the DAMP mission and show some results of the on-orbit performance, and then introduce some physical results, and with a summary. So basically, these are our scientific objectives. So the DAMP is essentially a cosmic ray and a gamma ray detector. So we would like to using the DAMP data to study the nature of dark matter particles using this so-called indirect detection method. Basically, if the dark matter can annihilate or decay into standard model particles, and these particles will be recorded as high energy cosmic rays by our detector, and we can use this data to try to infer the properties of dark matter. And of course, this data can be used to study the cosmic ray physics, like the acceleration, the propagation, and the interaction of cosmic rays in the galaxy. We can also detect gamma rays, so this data can be used to study the gamma ray astronomy, like this AGN, some neutron stars, supernova remnants, and so on. There are quite a number of particle detectors in space, including basically the magnetic spectrometer, like the Pamina satellite, and the AMS on board the International Space Station, and the other detectors are essentially the other detection, use the other detection technique. So basically they use the calorimeter method to detect high energy particles, like the Fermi gamma ray satellite, this CANIT instrument, again on the International Space Station, and the nucleon experiment, also this is ISS CREAM. Our DAMP mission was launched in 2015, in December 2015, and its altitude is like 500 kilometers with an inclination angle to 97 degrees. Its period it's 1.5 hours, and the orbit is a synchronous orbit. This is our instrument. So we have 4 sub-detectors. On the top is this is a PSD, the plastic scintillator detector. This is basically a charge detector. Can measure the particle charge using this DDX in the scintillator. And it can also be used as an anti-coincidence detector for gamma ray photons, because gamma ray is do not have charge. The second one is a silicon tracker detector. It basically to measure the track of a particle, and it can also be used to measure the charge of particles. We have some tungsten plates in the SDK, and this can be used as a photon converter to convert a photon, gamma ray photon, into a pair of electrons and positrons. The third one is a calorimeter with this BGO material. This is to used to measure the energy of a particle, and can be used to do this particle ID. In the bottom there is a neutron detector. So this is can be also used to for particle identification. So basically to separate the electromagnetic particles from the hadrons. And some more details about each detector. So the PSD, basically the size is here, and it has an area like 82 centimeter times 82 centimeter. So this is a basic parameters. And the geometry looks like this. We have two layers placed in, one is in X direction and the other is in Y direction. And this is SDK. So in total, we have 6 big layers of SDK. And for each layer, we have X sublayer and a Y sublayer. So this can be this can measure both the X coordinate and the Y coordinate of an incident particle. So we have 3 tungsten plates here. This can enhance the photon conversion probability. The total thickness of the SDK is about 0.8 radiation length. And this calorimeter, the weight of calorimeter is about 1 ton, and the detection area is 60 centimeter times 60. The neutron detector here, so we basically use this this boron capture of neutron to detect neutrons, and the basic parameters here. So this slide just show how we can distinguish different particles with this calorimeter technique. So for electrons and gamma rays, basically we use the charge detector to distinguish them. So in the calorimeter, their behavior actually very similar. And for electrons and protons, both have absolute charge 1. So we have the same signal in the charge detector, but their cascade behavior in the calorimeter is quite different. The electron will give an electromagnetic shower, and it looks more compact, looks regular. But for protons, it will give a hadronic plus an electromagnetic shower. So basically, it's a hybrid shower, and this looks more extended with some irregular structures. So we use this image difference in the calorimeter to distinguish these particles. And for heavy nuclei, we can measure their charge, so they can be separated with the charge measurement. So after its launch, DAMP has operated on orbit for up to now, it's for more than 5.5 years. For each half year, it will survey the full sky. So currently it surveyed the sky for 11 times and recorded more than 10 billion events. So the event rate versus the time, so keeps a very good linear relation. So it means that the detector works stably. So this is our charge measurement with the PSD detector. So we can see this charge peaks of the main elements in the cosmic rays. So from the hydrogen to iron and even nickel. So we can identify these particles in the cosmic rays. This is the performance of the direction measurement. So we use some gamma ray point sources to calibrate the PSF or the point spread function of our detector. So we use, for example, we use the pulsars, or we use some the AGNs to stack the events from a series of AGNs and to give these results. So basically, we find that the angular resolution at 10 GeV is about 0.4 degrees, and at 100 GeV is about 0.2 degrees. So for the energy measurement, we use this so-called MIP event, the minimal ionization particles to measure the energy. And to compare the results with the Monte Carlo simulation, we can determine the energy scale of our measurements. And this subplot shows the P side and the N side energy correlation. So for each BGO crystal, we have two-side readout, and these two sides have different gains. So we use this one to give a cross check of the energy measurement, and can also extend the dynamic range of the measurements. So this plot shows a linearity of our measurement. So we choose the events and we choose the event with a maximum energy deposited in one single BGO crystal, and to give this correlation with the total energy of this event. And this shows again a good linear correlation. So that means that the energy deposition in the calorimeter do not have a very significant saturation effect. And finally, we get this energy resolution about 1%. So this for events around the TeV energies. We have done some comprehensive test beam validation of the measurements. So this for the electron beams from 0.5 GeV to the highest one, 243 GeV. After some correction for this data area of the detector, so we can get a very good recovery of the beam energy. This plot shows the energy resolution. So again, it can reach the level of 1% at high energies, around 100 GeV. And this is the performance of the particle identification. So basically for electrons and protons. So we defined two variables to characterize its the morphology of a shower in a detector. So this one is for the lateral distribution, and this one is for the longitudinal distribution. So basically, we find that we identify that so this part of particles, this population are candidate electrons, and this population are candidate protons. So a combination of these two variables gives this one-dimensional distribution. So we find that if we have 90% electron efficiency, the proton background, so here, this is green, the events under this green line, the proton background is very tiny, it's about 2% at TeV energies. And at higher energies, this background increase somehow to, for example, 10% at 5 TeV. Again, we use some beam test data to validate this particle identification algorithm. So this is a proton beam. So the distribution of proton beam and the Monte Carlo simulation agree well. And this is for electron beam. So this zeta parameter, just the previous one, so this parameter, this is zeta parameter. Also, we use the gamma ray photons to validate this method. We know that so we can use the charge detector to select the gamma ray events from the sky, and this is the distribution of the gamma ray events. So if we look at the, we find this structure, we are confident that these events should be gamma rays. And we know that the gamma rays will have similar shower behavior with electrons. So we overplot the gamma ray data on this plot, and we find that they indeed quite consistent with the electrons. So this is our results published a few years ago about the measurement of cosmic ray electron plus positron spectrum. So the main result is that we find a spectral break at 1 TeV energies with a very high significance. And currently we have actually 3 times more data, and the analysis is still ongoing, and hopefully in the near future we will update the results with much more data and much higher precision. These are results of the cosmic ray protons spectrum measurements. So this top panel shows the charge distribution of left one is proton and right one is for helium. So we can separate these particles quite well in even to the very high energies. So this can enable us to give a precise, give us a pure sample of protons. And this results shows our measured proton spectrum in a wide energy range. And we found that there's 2 prominent structures. The one is a hardening feature around 500 GeV and a softening feature around 14 TeV. And recently we published the helium spectrum. So again, we find this interesting spectral features, a hardening feature here and a softening feature at higher energies. So if we compare this proton and helium spectrum, we found very interestingly that their spectral shape looks quite similar with each other. And this spectral structure seems to have a nearly Z-dependent have a Z-dependence. So this could be quite interesting in understanding the physics of this, the origin of these structures. And so these are our preliminary results about the boron to carbon ratio. So this quantity is quite important in understanding the propagation of cosmic rays. And so currently our analysis is limited in this low energy range. So because at high energies, the quite amount of simulation are necessary, and we are still on this work are still ongoing. We analyze the anisotropy of cosmic rays. Unfortunately, due to the limited data sample, so currently we do not observe significant anisotropies of cosmic rays, and we derive an upper limit to a level of 1 to a level of 10 to minus 3 for energies higher than 100 GeV. So DAMP has a very high energy resolution, so it should be very good for the search for gamma ray lines. So we did such kind of research with DAMP data, and it turns out that we can give the most stringent constraints on the. So we do not find a significant line emission in our gamma ray data, and we give the most stringent constraints on the dark matter annihilation cross-section or decay lifetime. the results basically shown here. It's actually it's even better than the Fermi results with more data. So what is the implication of this line search? So basically, we applied our results on a model with under this NMSSM model. So this model was recently proposed to explain this G-2 anomaly, the galactic center axis, GV axis, and the antiproton axis. So basically, the model gives this line, this parameter space here, the dark matter mass, and this annihilation to gamma cross section here. So unfortunately, the current limit from this line search is not sensitive enough to probe most of this parameter space, and the possible improvement in future may probe or part of this parameter space. We observed Fermi bubbles independently, and the results looks quite similar with the Fermi results. And this is our gamma ray catalog. So currently we have detected like 2,050 gamma ray sources, so including different source types. We also studied some phenomena in the solar system. So like this is an example of a Fourier decrease event. So when there is a solar flare, so we can observe the decrease of the cosmic ray electron events. So this is so-called the Fourier decrease. So from the damper analysis, we actually find some new features of the, for example, the recovery time of this Fourier decrease. This shows the recovery time versus the energy. And the previous measurements by Pamina shows this kind of behavior, some rising with energy, and the damper data shows the declining behavior here at higher energies. So this is quite interesting in understanding the physics of the Fourier decrease. So I come to my summary. So the damper detector works smoothly for 5+ years and opening a new window to look at the high energy universe above TeV. And we measured the electron plus positron spectrum, find a spectral break. And we measured the proton and helium spectrum and revealed the interesting structures. We obtained the stringent limits on the dark matter annihilation or decay parameters into monochromatic gamma rays. And with more results about cosmic rays and the gamma rays are coming. Thank you for your attention.
Okay, thank you very much. So very nice talk. So any questions or comments? Okay, so if not, so I'd like to thank Professor Qian Yuan again. So thank you very much. Okay, thank you.
Okay, thank you.
Okay.
Thank you.
That's the end of this session. So let's thank all the speakers again. Okay. Thank you. Thank you all. Okay.
Thank you.
Thank you.
Bye-bye.